In this video, we're going to re-explore the concept of hydrates, but now we're going to embed the concepts of moles and percent composition within as well. We've actually seen hydrates in a previous unit where we learned how to name hydrates and we learned how to define what they are as compounds. So what we're going to do in this particular lesson is we're going to learn how to calculate a hydrate formula and solve problems that involve hydrates. So here we have an example of hydrates. This is the hydrated version of a compound. And then if you remove the water, well, it becomes this white color over here. Different hydrates will have different colors, but you can remove water in some way, shape, or form, and then you'll get a different color. And if you add the water, you'll get the original color with the water in it, as we saw before. So just a quick reminder, hydrates are ionic compounds with water embedded in their crystal structure. And we represent that by putting the ionic compound formula here and then a little dot to show that there's water connected to it, and then a number of waters in that formula unit. And then to name it, we would simply name the ionic compound, so calcium chloride, and then you'd say how many waters you have. So 6 is hexa for the Greek prefix hexa, and then the water part is named as hydrate. So calcium chloride, hexahydrate. In your handout, there's a link to the lesson we first did on hydrates. If you forgot how to name them, you can go back and check that out. So the hydrated version of a compound contains the water. If you remove the water, then you have what's called the anhydrous version of the compound. So here we have magnesium sulfate heptahydrate. If you were to heat up the hydrate and remove the water, you now have magnesium sulfate, and you could further specify that it's not the hydrated version by calling it the anhydrous magnesium sulfate. So how do you convert a hydrate to its anhydrous form? Well, you simply heat up your hydrate. So, for example, here I have the hydrated version of this copper sulfate hydrate over here with blue crystals. I apply heat to it, and when I apply heat to it, the water molecules leave as gas, and then I'm left with the white powder, and this is the anhydrous. And the really neat thing is that you can actually use this method to figure out what the hydrate is. In other words, you could weigh your hydrate before you heat it up, and then weigh it after. And basically, it should weigh less. And why does it weigh less? What did you get rid of? That's right, you got rid of water. So the amount of water you got rid of can be determined by doing the difference between the initial mass of the hydrate and the final mass of the anhydrous. And then you can use that to figure out how many water molecules must have been attached to your formula unit. And so that's essentially what we're going to see in this lesson. We're going to see how can you do a hydrate analysis to figure out what the actual formula is. How do we know what that X value is? Is it hexa? Is it hepta? Is it octa? Using this idea of heating up and then finding the difference in the mass between the beginning and after complete heating. There's a demonstration for that over here. So if you click on the link here, you'll see a great demonstration that illustrates this hydrate analysis. And you'll hopefully have the opportunity to do a lab where you'll get to do a hydrate analysis as well. So there are some essential skills we need to do before we move on to a full hydrate analysis. We need to be able to write dehydration reactions for hydrates, and we're going to do some examples together. You also need to be able to calculate the molar mass of a hydrate, and which is pretty straightforward. Luckily, if you can do molar mass already, it's just kind of an extra step that you have to do here. And then we have to be able to calculate the mass percent of water in hydrates as well. Once we can do the mass percents, the molar masses, and write those dehydration equations, then we can go and do a full hydrate analysis to determine the formula of a hydrate. So we're going to start off with the dehydration equations. And so essentially you can write a word equation or a balanced equation. And what you do is you write the name of the hydrate, you put an arrow. Generally you write heat on top of the arrow to show you're heating it up. Then you put the name of the anhydrous salt and then plus water. If you were doing this as a balanced equation, you'd write the formula as a solid because you're heating it up as a solid. Put an arrow, put heat on top, and then you'll write your ionic compound as a solid, and then your water as a gas, depending on how much water left. The X matches the X over here. So let's go do a few examples in our handout, and then also we'll do some examples of molar mass and mass percent of hydrates. So here we have, let's fill in our blanks to what we remember. Hydrates are ionic compounds that contain water molecules in their crystal structures. Water, in other words, H2O in symbol words, in formula words. I shouldn't say formula words, in formula, because there's no words, just formula. So we have CaCl2.6H2O. This is an example of calcium chloride, hexahydrate. The hexa comes from the fact that there's 6 over here. If you don't remember how to name and write formulas for hydrates, you can review it in the link in your handout over here, which links you to a previous lesson we did in earlier units. The anhydrous version of a compound is the ionic compound that remains when water is removed from a hydrate. When you remove the water from a hydrate by, let's say, heating up the hydrate and then causing the water to evaporate. So this is the hydrated version of magnesium sulfate. This is magnesium sulfate heptahydrate. And then this is just regular magnesium sulfate with no water in it, and that's called anhydrous. So how can you remove water from a hydrate? Well, you can do so by heating it up. So here's your hydrate to begin with. You heat it up, and then the water will leave in the form of gas. And then what you can actually do is you can actually figure out how much water left by doing the difference in mass between the initial and the final. So if you look here, initially my hydrate weighed 0.2166 grams. Once I did a full heating, my substance now weighs 0.1353 grams. So we lost some mass, and that's because we lost a lot of it as water. And if you want to find how much water was contained in there, you can simply do, so if I were to write mass of water is equal to your 0.2116 grams minus your 0.1353 grams. And you can find how much water you had in that hydrate sample. And then you can use other math and other techniques to figure out 5639 to figure out the value of X that you would have over here, and we'll learn that in more detail after. But it's important that when you're doing this lab that you heat up the hydrate completely. If you leave some water behind, you'll underestimate how much water you had in there. So when you do this lab, you need to follow the instructions to see how long you should heat it up for in order to allow the water to escape 100%. And you need to make sure also when you're heating it up, you don't spill any of the original solid. Otherwise, you'll overestimate how much water you have because you'll mistakenly say more water left than actually did. But you'll learn more about that as you watch the demo and as you read through procedures for hydrate analysis. So we have our dehydration equation. That's our first skill we have to be able to do. Write a word equation and balance equation for the thermal dehydration of magnesium sulfate heptahydrate. Show all states. So we'll start with a word equation. What I do first is I write out the hydrate, so magnesium sulfate heptahydrate. I'm going to draw an arrow and I'm going to write heat on top. Now you don't have to write heat. You could also put a triangle. The triangle basically just means heat. So triangle equals heat. You can choose either one. Just understand the triangle means heat. And when you do that, you're going to get magnesium sulfate produced. Magnesium sulfate plus water, because the water is now removed from the magnesium sulfate and heptahydrate. So this is basically the anhydrous version, and this is the hydrated version. Now, if you want to write a balanced equation, you would need to remember how to make formulas for hydrates. So first you do your ionic compound, magnesium sulfate. Remember, I'm just going to do the work over here. Magnesium sulfate, magnesium is +2, sulfate is -2. It's one of your polyatomic ions. You can crisscross and then reduce. So Mg2SO4 2, reduce, and you get MgSO4 dot heptahydrate. That means there's 7 waters from the hepta. That's from your Greek prefixes. And then this needs to be written in its solid form because you heat it up when it's in solid form. We'll make an arrow just like above with the little triangle or heat written on top. And then we'll get magnesium sulfate, which is just the ionic compound part. And it's still in the form of a solid, plus water. And it's going to match how much water you had in here, assuming you heated it all up 100%. so plus 7 H2O, and this is in the form of gas because it's heated up and evaporates away. And so we've just shown a dehydration equation for magnesium sulfate heptahydrate, and all the other hydrates will follow essentially the same format. So if you can do this example, you're able to do other examples as well. And that's our first skill that we need to know. Our next skill that we need to know before we go into more complex problems is calculating the molar mass of hydrates. And really to do that, it's not really any different from doing regular molar masses, except you need to take into consideration that you actually have more waters than just one. So your first step is find the molar mass of the ionic compound part. Your next step is find the molar mass of the water and not forget to multiply it by the coefficient in the front. And then afterward, just add the two together. So for example, here I have the molar mass of magnesium sulfate heptahydrate. First, I'm going to find the molar mass of magnesium sulfate using your periodic table. So we know that we have magnesium is 24.31 grams per mole, plus sulfur, which is 32.07 grams per mole, and that's from the periodic table. Plus there's 4 oxygens times 16 for each of them, grams per mole. And we get, let's try that out here, so 24.31 plus 32.07 plus 64, and we get 120.38 grams per mole for the ionic part. Next, we have to find the molar mass of water and multiply it by 7. So essentially we're doing 7 times the molar mass of H2O. If you do enough practice, you'll find that the molar mass of H2O, so let's do this here, 7 times the molar mass of H2O is 18.02, and the reason is because there's 2 hydrogens, so 2 times 1.01, plus 1 oxygen, that's 16. And that gives you 18.02, but you have 7 of them, so you need to make sure you're doing 7 times that. And that's in grams per mole. And so 18.02 times 7 gives us 126.14 grams per mole. And our last step is simply adding the 2 molar masses together. So molar mass of the entire hydrate is going to be 120.38 grams per mole plus 126.14 grams per mole, and we get 246.52 grams per mole. I always like to do a double check just before I finish off to make sure I didn't make any errors. It seems like this is correct, but just quickly again, magnesium is 24.31 plus sulfur 32.07 plus 64 for the oxygen, and then plus 7 times 18.02, and I get 246.52 grams per mole to 2 decimal places because that's what my molar masses are given to in the periodic table. So let's try one more example. You can try this one yourself first, and then check with the video to see if you're on the right track. There's also another little video answer provided here if you'd like for both of these problems, so you can see it done from a different perspective. So calculate the molar mass of copper 2 sulfate pentahydrate. The main thing here is that you're not given the formula and you need to know how to figure that out. So that's my first step this time. First, I have to find out what copper 2 sulfate is, and if you do your crisscross, just to show you over here, we have copper plus 2, sulfate minus 2. Crisscross or charge balancing both work. You crisscross it, you get Cu2SO4 2, and you reduce by dividing by 2. And so we get CuSO4, and then dot. It's a pentahydrate, so 5H2O. So now that we have our formula, the next steps are essentially the same. Find the molar mass of the copper sulfate, CuSO4, and just to show you, once again, where you find your molar masses. If you don't remember, you go to your periodic table at the top of our calendar here, and use ours because different periodic tables will give you different decimal places. So it's good to use a consistent one because that's what I base my answers off of. So copper is 63.55. I forget that one quite a bit. 63.55. Is that what I said? Let me just double check again. Yes, 63.55 grams per mole. So 63.55 grams per mole plus the sulfur, which we said was 32.07, but let's just confirm. Sulfur, that's right, 32.07 grams per mole. Plus the 4 times 16.00 grams per mole. And so that's going to be 63.55 plus 32.07 plus 64 gives us 159.62 grams per mole. So 159.62 grams per mole. Now we just have to do our molar mass of our waters. So we have, but times 5 because there's 5 of them. So 5 times the molar mass of water, which is 5 times 18.02 grams per mole. And that gives us, so 5 times 18.02, 90.10 grams per mole. Now we can add the 2 molar masses together. So molar mass of the complete hydrate is equal to 159.62 grams per mole plus 90.10 grams per mole. And we get, so plus 159.62 to 49.72 grams per mole. I'm just going to verify quickly doing the calculation again. So 63.55 plus 32.07 plus 64 plus 5 times 18.02 gives you 249.72 grams per mole. And that is our molar mass for the hydrate of copper 2 sulfate pentahydrate. So far, what we've seen is how to write the dehydration equations, or which we will sometimes call thermal dehydration. That basically means dehydration using heat. We also saw how to do molar masses of hydrates. And to do that, you had to have the basic skill of knowing how to make formulas for hydrates if you were given the name. And again, if you don't remember that, you can always review that in the lesson provided here from one of our previous units. So the last skill you really need to know is related to the mass percent of water in hydrates. And then after we have that last skill, we can go to do formulas for hydrates because we'll have all the skills required. So we'll do the mass percent of water in hydrates in the following video. And then after that, we'll go and do a full hydrate analysis.